The first thing you want to do when taking the limit of any equation is plug in the given value for x into the function. For example, in the function 3x squared over x cubed, we are trying to find the limit as x approaches 4. As seen, you plug it into the equation 3x squared over x cubed, and you get 48 over 64, which reduces to 0.75 or 3/4. This is the answer. This is the limit. That is the most simple method, and that is the easiest way to find it. Then, another method to take the limit is graphically. When looking at a graph to find the limit, you must first have an accurate graph, such as through a graphing calculator. You take the same function, the same equation, the same number, and you go and see at that x value what the graph approaches. For example, in 3x squared over x cubed, for x approaches 4, you see that the graph is going towards 4 from the left and towards 4 from the right. Therefore, the point x equals 4 approaches 0.75 again. As seen on the graph, 0.75 is approached from the both sides. Therefore, the limit exists at that point. When looking at a graph to find the limit, you may also notice when the limit does not exist. When, for example, the graph has a vertical asymptote, or when the graph approaches different values. For example, this one approaches negative infinity and positive infinity. Therefore, the limit does not exist at that point. In this one, the limit is equal to 2 because the limit approaches 2 from the left and from the right. Although this point is the value, the limit does not have to equal this point, so therefore this is not the limit. The graph shows that the limit as x approaches 2 is equal to 2, even though the actual value at x equals 2 is 4. The value 2 is approached from both the left and the right. The limit as x approaches a for f of x does not have to equal f of a. The more complex method of taking a limit is algebraically. When taking a limit, one may have to solve in a different manner. When the number or value you plug in gives you 0 over 0 or infinity over infinity, it is considered the indeterminate form and must be solved algebraically. Example 1. The limit as x approaches 7 for x squared minus 3x minus 28 over x squared minus 6x minus 7. This equation right here. You plug in 7 and you get 0 over 0. This is indeterminate. You then have to factor in order to get the limit. Once factoring, you get x minus 7 times x plus 4 over x minus 7 times x plus 1. The x minus 7s cancel out to 1. Once you take that out, you plug it in again, and you get the limit as x approaches 7 over x plus 4 over x plus 1, and you get 11/8. This is the limit and the answer. Another algebraic method is multiplying by the conjugate. An example for multiplying by the conjugate or solving algebraically as in a conjugate is the limit as x approaches 13 for the square root of x minus 4 minus 3 over x minus 13. When there is no polynomial to factor, it is necessary to multiply by the conjugate. The polynomial cannot be factored, therefore you have to multiply by the conjugate. In this example, the limit as x approaches 13 of x minus 4 square root minus 3 over x minus 13 is multiplied by the conjugate, which is x minus 4 plus 3 over the square root of x minus 4 plus 3. Therefore, the equation is still equal to 1, but is being changed. The conjugate is simply the numerator with a switch sign over itself to keep it at 1. Upon multiplying by the conjugate, you get the limit as x approaches 13 of x minus 4 parentheses plus 3 times the square root of x minus 4 minus 3 of the square root of x minus 4 minus 9 over x minus 13 over the square root of x minus 4 plus 3, which then reduces in turn to the limit as x approaches 13 of x minus 13 over parentheses x minus 13 times the square root of x minus 4 plus 3. You can then cancel out x minus 13 and it gives you 1. So it'd be 1 over. Then it gives you the limit as x approaches 13 of 1 over the square root of x minus 4 plus 3. You plug in 13 to that, which then in turn gives you 1 over 6, which is the limit and the answer. The third method of taking the limit of an equation is numerically. This process is similar to graphing, however, uses a table instead of a graph to see what is being approached from both the left and the right for a given function. Example 1, the limit as x approaches 10 for x squared plus 1 over x plus 1. We're trying to find the limit as x approaches 10, however, we're going to act like you cannot just plug in 10. So you use a table. You find 3 points that get closer and closer to 10 from the left, and 3 points or 2 points that get closer and closer to 10 from the right. So 3 points bigger, 3 points smaller. So we chose 9.9, 9.99, 9.999, 10.001, 10.01, which give us the values 9.083, 9.1719, 9.1808, 9.1828, 9.1917 respectively. If you were to actually plug in the value for the limit as x approaches 10 into the equation, you would get 9.1818. And you can see by the table it is being approached from both the left and the right at this value. Therefore, that is the limit. This is the answer. Numerically is just looking at the graph, but in table form. Finally, we get to L'Hopital's rule, which is the calculus theorem, and it says, when given the indeterminate form, another option is using L'Hopital's rule. The rule states that when you get 0 over 0 or infinity over infinity, you may take the derivative of both the top and the bottom to find the limit and plug in again. If you plug in and receive 0, 0, or infinity over infinity again, you may use the rule again. Example, the limit as x approaches infinity for 8x squared over 32x squared. When you plug in infinity to this equation, you get infinity over infinity, which is indeterminate. You then use L'Hopital's rule, and you get 16x for the top derivative and 64x for the bottom derivative. You then plug in the infinity for x again into the equation, and yet again we get infinity over infinity. So then you do L'Hopital's rule again, and you get the limit as x approaches infinity for 16 as the top derivative over 64 the bottom derivative, which you then may reduce, because that is the answer, to 16 over 64, or 1/4. These are both the limit as x approaches infinity and the answer. This AP question was brought from the 2015-2016 AP BC practice exam on College Board's website. The question goes, the limit as x approaches infinity for the square root of 9x to the 4th plus 1 over x squared minus 3x plus 5. When you plug in infinity, you get infinity over infinity. This means you may use L'Hopital's rule. When you take the derivative first, you get the limit as x approaches infinity of 1/2 9x to the fourth plus 1 to the negative 1/2 times 36x cubed. You have to use a chain rule on the top. And then you get, on the bottom, the denominator is equal to 2x minus 3. You plug in infinity again, and you get infinity over infinity. You then use L'Hopital's rule again. And you take the second derivative of the top and the second derivative of the bottom. When you take the second derivative of the top, you get negative 1/4 times 9x to the fourth plus 1 to the negative 3/2 times 36x cubed times 36x cubed plus 1/2 9x to the fourth plus 1 to the negative 1/2 times 108x squared over 2. You plug in infinity again, and you get infinity over 2, or infinity. Therefore, the limit does not exist or is undefined by unbounded behavior, because the limit as x approaches infinity for f of x is equal to infinity and is unbounded.